That's our goal, essentially, just show you how we did it. And I want to show you, if you didn't do it, you probably didn't have any idea what this actually, but everybody tried it, which is great. So now I'm going to show you. So I put f there like this. So then I will have the px, gx, and then multiplied by f. Now remember, whenever you have operator in the front, these two terms are effective. It doesn't matter. So essentially, you have to put a parenthesis in the front like this. And the second term is g, x, px hat, f like this. So that would be always the case. Now, when you have a situation like this, we're going to work on the first term first. So the first term is going to end up with a negative ih bar, partial, and g. That's applied on the g only. So, and then put a parenthesis around it. In other words, this derivative, partial derivative, only applies in g, not f, for this term for the moment. And now, next step, and I'm going to continue on this equation. This time is p is going to apply to f. So the g is pulled out. So the g is pulled out, and then this term is applied to f. So we'll do a px f like this. So essentially, my first term will split into these two terms. Are we good? Now, this will split into these two terms. Let me check the quality of the reading. Yeah, so these will be split into two, and that's what you're going to see them. Are we good? Everybody's good? Good, everybody? Okay. So now we have a minus g of x, px, hat f, like this. That's my second term. Now the second term, you see the second term and this term, they're exactly the same. So then these two is going to cancel it out. So that's this exact same split. In other words, the first box, second box always cancel one terms because it just swapped over. That's why I always cancel one single terms like this. So now my final expression will be partial g over partial x and f, like this. And this is the final results. Now, since my f is arbitrary, so therefore the brackets here, the commutator here must equal this term. So in other words, so this is a px hat, gx, and this has to equal partial g over partial x. That's the commutator you have. You can check whether this is actually correct or not. If you replace g of x by x itself, if you replace gx by x itself, so now if g of x equals x, then my right-hand side, this will be negative ih bar, like this. Now you see px equals a negative ih bar. This guy is x in the front, p behind is a positive ih bar. You see, they must match. I always found it interesting. You can test to see whether actually my calculation is correct. So all I need to do is just replace this g of x by x, and you get everything you need. In the future, if you have an extra term like this, x squared like this, let's go to g of x like this. If you have an x squared like this term, folks, please do not be scared by this. This is if you have something squared or two terms multiply each other, you're going to use a rule as we did before. In other words, if this happens, what you do is you pull the px, one px out, one px out, and the second add px, second px in the back, second px back. So that's why I ask you guys to remember A multiplied by B, comma C, and equals whatever the term that you need. So this multiplication is so crucial. Did you see why I need to introduce these crazy things like this? Did you see why I introduced this? Because if you have a square, if you do directly use the square to do the calculation like this, you'll be there's so many terms. Make sense? Make sense? So that's the beauty. All right, some of us have got any questions so far? Okay. Now, are you ready to Heisenberg Uncertainty principle? You ready? Let's go. And this part is quite crazy. So everybody should learn the Heisenberg Uncertainty principle. Heisenberg Heisenberg got this idea even before the quantum mechanics was formally introduced. And he got this wonderful idea. He did not know what's the consequence of this. So this is called Heisenberg Uncertainty principle. Heisenberg Uncertainty principle is one of the very important climax of quantum mechanics. If everybody tells you that quantum mechanics is about matrices and this is where you're going to learn the quantum mechanics this way, and this is so important, and we cannot emphasize too much on this, the value of this particular explanation. Since the entire derivation slightly complicated, I want to show you the simplest possible explanation to you in the beginning. Show you the results, and later I'll show you how we get this result. The uncertainty principle refers to two things. My delta A is a measurement, how large uncertainty this measurement you got. I will define what this delta A shows. I have a delta B terms multiply each other. So the uncertainty quantum mechanics says you cannot be zero. You always have to be larger or equal to the h bar over 2. So this is the uncertainty principle. Now I'm going to explain what this delta A is. Delta A is just the standard deviation itself. It's the exact same defined the same way. And this is a square root. The operator squared, or quadratic operator squared, not operator, the operator squared, and then the expectation value of this operator, minus the operator expectation itself, and then put a parenthesis squared. And this definition is the standard error definition, exactly the same when we define it. In your experiment, you always have square this particular one and then minus the square. Have you ever seen this expression before? Have you seen this expression before? You have seen them? So this is how do we define it. Did you see we have brackets here? Did you see our brackets here? This bracket is a state. And this state is not an arbitrary state. Let me put a phi here. This is a quantum state. This quantum state must be physical quantum states. For instance, if you look at some textbooks use the wave function look like a psi equals x. This is wrong. You cannot use this one. If you use this one, the uncertainty principle will give you wrong results. So in other words, this must be physically quantum state. Now next one, I think almost all the book, most of these books did not mention this second item. Could you guys write this down? Absolutely write this down. This state cannot be an eigenstate or eigenfunction, whatever you call it, eigenstate of either A or B hat. So this one here, this particular psi, when you plug in the brackets over here, it cannot be the eigenstate of this either operator or eigenfunction of operator A or operator B. You cannot do it like that. Because if you do, this guy is going to be 0 immediately. If this is 0, but 0 cannot be larger than h bar over 2. So that's the problem. So this, you cannot be the eigenstate of either A or B or both. Doesn't matter. You cannot do it like this. So for this reason, it's going to be very restricted, such way that when you got this point here, it will be very important. And I want to show you the consequence of this. The consequence of this. So this consequence of this essentially just tells you that the A and the B, if it commutator A and B, if they equal 0, sorry, you cannot use it. In other words, if A and B equals 0, you cannot use it because there's no uncertainty involved. So I'm going to write this down. If the commutator equals 0, this does not apply. This does not apply. So this only means that you can determine these quantities 100% without any uncertainty. So this doesn't apply. So A, B can be determined. Theoretically, 100%. If they equal 0, sorry, the story ends here. So there's no need for use uncertainty principle. This is valuable if the A and the B not equal 0. Like our position and the momentum in this case. You see, position and the momentum, they not equal 0. So that's why they will tell you that if uncertainty principle just tells you the position and the moment cannot be measured, and this example, and then applies. So here are some examples like a position and momentum, and angular momentum, and these ones you cannot measure both quantities simultaneously with exactly 0 uncertainty. So with the certainties in this case. So these will be applied. So that's what happened. And experimental facts a lot. And let me show you experimental facts. And here quickly. So this is one of the experimental facts is that if you put let's say the slit size becomes much narrower. So suppose I move this slit a really small slit, which means you want to confine my x is a very narrow region. Then the momentum region is going to spread out. In order to spread out, you will see when you make this guy smaller and smaller, and the wave is going to be extended real big. So on the back side of your screen. If you make this even smaller, it's spread even further because you have a momentum now becomes even more undetermined. So this is the experimental fact. And I want to show you some steps, not entire steps, but some steps of this entire calculation. How do we derive it? So it consists of 3 steps, basically. And we won't show you all these details, but I want to show you the steps. Step number 1. So this is the step number 1. How do we prove the Heisenberg Uncertainty principle? We start with the wave function, let's go psi, like this. And this psi is not arbitrary. It should be confined with both of these operators involved. And this confined with the alpha A hat plus I B hat. So these are the operator, and I'll apply another wave function. So like this. So essentially, we start with this particular wave function, so that is what we want. Now here you see we have alpha. This alpha is real. And imaginary, so this is imaginary terms here. So that is the starting point of the wave function. The second step, what we are going to use, we'll use the property of the probability density. We know this guy is a probability density, so probability density. Now, here is the quantum mechanics start. Here is the physics start. So this is the physics step. So here's the physics step start. So the quantum mechanically, the probability must be larger or equal 0. You can be 0, of course. must be larger than 0 normally. So that's the equation you're going to see them. So then this leads up another equation, quadratic equation. I will explain this to you. The quadratic equation looks like this. A alpha squared plus b alpha plus c larger equal 0. So in other words, if you do this step, you will end up with this particular equation. Now, this is purely mathematics now. Did you see we have this equation here? If this equation is larger or equal 0, so therefore it is the indeterminate, it should be equal to b squared minus 4ac less than 0. Because it says that this guy has no solution on the x-axis. Essentially what this is, it looks like this curve. This is the alpha. Curve will look like that. So essentially we'll end up with this particular curve like this. So then this has no roots. You have this determinant you will end up with. And that is the second step. And one last step, we use this relationship. One last step, we use this relationship will be 4ac larger or equal b squared. Yes, question?
Is there a reason you're only using the square root of the quadratic formula instead of the whole thing?
You mean why we get this quadratic equation?
No, like to find the roots, you have b squared minus 4ac. Is there a reason you're only using the square root part of the quadratic equation instead of the whole thing?
I did use the whole thing, Jeffrey. Let me show you the root. This root alpha is over here. I hope I understand your questions here. The solution to this equation here, solution to this, if this has to be 0, then my alpha just equals 2a negative b plus minus square root like this, right?
Yeah.
So
I was asking why. Oh, okay. I think I get it now.
You get it? You get it?
So the uncertainty part is specifically the square root part.
Exactly,
Okay.
exactly. You know, we do not need to use this entire term. All we need to use is this delta thing. And then when this delta thing comes out, the problem with that, did you see here? My alpha has to be real. That's what alpha codes are. So if this alpha is real, so then you can be sure which part it has to be the really correct. So this is essentially the trick that I used. So now did you see you have a larger equal b squared like this? And this larger than equal b squared is just this guy's here. It's just this guy's here. So these two are just come from that one. Now you may wonder, what is my a, what is my c, what is my b squared? And this is all in the book, of course. And what I want to show you immediately now. So this entire term is going to equals, so you know it's starting from, just basically starting from this one here. And this is going to be translated into delta A, delta B, larger than equal. And so we essentially take square root of both sides. Folks, so let's take square root of both sides. Take square root of both sides. That's what we did, take square root of both sides. So then you will notice that when we take square root of both sides, and then this is going to equals phi a hat b hat phi like this. And this take the square root like this. So this is the entire derivation. When I give you, show you all the details, of course you can look at the book and how all the details are presented. So essentially we start with a wave function like this. We make sure this alpha is real. We put an imaginary I there. When we write this book, I thought, well, can I just simply use the real ones? Sorry, when you get real ones, it's so messy. You cannot do it like this. And can I just assume this is imaginary without using the real complex one? When you assume this guy is imaginary, then this equation doesn't work anymore. Because if this guy is imaginary, it can choose any root it wants. So you didn't have this relationship. So and then I say, oh, sorry, that's why people never tried this. Well, they probably tried it, they did not tell you. And that's what they tried, and of course all failed. And then this is the only way you're going to learn these things. So then you will get this uncertainty principle. Now watch out, folks. You see, if the commutator here equals 0, then the whole thing just falls apart. You cannot do anything with it. So that's why these two must be not equal 0, like this. Otherwise, the thing that you learn is basically cannot be used for the uncertainty principle. This is the shortest ever uncertainty principle you're going to learn, because I don't think the mathematics involved should play a significant role. Just show you how the details are. You start with this. Now you also notice that these two, the phi and the psi here, cannot be eigenstate, because this guy's eigenstate, this entire thing is just a number now. Because eigenstate is 1 plus 1 applied on that, that's going to be 0. Any questions before I close today? Okay. On Friday, we're going to review our exam, number 1. And if you guys have any questions, and please let me know. And I expect the following. If you are preparing for this exam, and make sure you do go through all the homeworks, quizzes, and for those ones that we cannot quiz you everything, but we will quiz you those parts we think is quite important. All right. So essentially, I want to give you a heads up, and it will probably span about maybe 20 to 20 minutes around on Friday. We'll explain part of that. And the concepts I already posed the concept, right? Post concepts already. You download the concepts. I strongly suggest you go through these concepts immediately right now. If you see any concept you want to explain it on Friday, please do so. On Friday, I will focus on a few problems, so that way, problem part will be 50 points, and then conceptual part, I think, is also 50 points, and add up to 100 points. You will see 5 questions, ask you conceptual questions, and 2 problems, essentially 2 problems. And this is similar to our sample exams. You can look at the sample exam. If you want me to explain the sample exam, please let me know. Okay, I will get ready for that as well. So if you want me to explain the sample exam, please do let me know. Any questions? Anything I can help with right now? Nothing? Okay, very good. Do not forget about the homework turn in on Friday. So we're going to collect them. And I will assign the homework once you guys turn it in. So that will be in it.